Okay. So we're gonna do 6.4, which is Green's theorem. You can see your learning objectives here. We have the actual theorem for you. The proof for this is in your book. I did not want to pull it over. So there's that. We want to apply Green's theorem for flux across a circle. So let C be a circle of radius r centered at the origin. Let big F xy equal the vector xy. Calculate the flux across C. So we're going to let D be a disk enclosed by C. The flux across C is we could evaluate this integral using tools we have learned, but Green's theorem makes the calculation much more simple. So we're going to let P of xy equal x and Q of xy equal y, so that F is equal to the vector PQ. Note that Px equals 1 equals Qy. Therefore, Px plus Qy would equal 2. So by Green's theorem, we would have C, F, and ds over D to dA. All right, since this section is the area of a circle, then that means we would have 2 times pi r squared. So therefore, the flux across C is 2 pi r squared. I feel like that's one of those questions that they would throw on the SAT or something else and just be like, hey, intuitively, what do you think this answer is? And you would go with that because you wouldn't know any different. But it would be correct. Right? All right, so to calculate the flux without Green's theorem, we would need to break the flux integral into 3 line integrals, 1 integral for each side of the triangle. Using Green's theorem to translate the flux line integral into a single double integral is much more simple. So we're going to let D be a region enclosed by S. Note that P sub x equals 2x and Q sub y equals 1. So that tells us P sub x plus Q sub y equals 2x plus 1. Green's theorem applies only to simple closed curves orientated counterclockwise, but we can still apply the theorem because, let me write this out for you. and S, negative S, is orientated counter clockwise. So then by Green's theorem, we have this part equal to negative Notice that the top edge of the triangle is the line y minus 3x plus 3. Therefore, in the iterated double integral, the y values run from 0 to equal to y equal to 0 and y equal to negative 3x plus 3, and we would have, so that's just showing you how to use the how they get to the next step. So negative 0 to 1, and then 0 to negative 3x plus 3, 2x plus 1, dy dx. So then that gives us which is negative 5/2. All right, see, we're moving and grooving. Really big problems, but luckily they're not taking that much space. Okay. So applying Green's theorem for water flow across a rectangle, water flows from a spring located at the origin. The velocity of the water is modeled by the vector field. So find the amount of water per second across the rectangle with vertices oriented counterclockwise. So of course you know that we need that. You know at this point that we have to let C represent the given region, given rectangle, and let D be a rectangular region enclosed by C. To find the amount of water flowing across C, we calculate the flux. So we're going to calculate C V dot N ds. We're going to let P of X equal to, or sorry, XY equal to 5x plus y, and qxy equal to x plus 3y. So that V is equal to PQ. I'm sorry. So then is equal to 5 is equal to 3, which means px plus qy is equal to 8. So then that tells us, I'm skipping some steps because I think you guys can probably follow along with it at this point. So then that's 8 times the area of D, which the area of D is going to be that 5 times 2. So therefore, water flux is 80 meters squared per second. Now I will say that sorry, I didn't know that my camera was off the whole time. Apologies. I will say that apparently this is just all examples. All 9 of them are examples, but hey, that is good. So finding a stream function. Verify the rotation of the vector field is source-free and find a stream function of f. So note that the domain of f is all which is simply connected. Wow, it is super raining out. Therefore, to show that f is a source-free, we can show any of the 1 through 4 from the previous list to be true. In this example, we show that IM4 is true. So we're showing that then that tells us that p sub x plus 0 equals q sub y, sorry. So that would also tell you then that p of x plus q of y equals 0. So therefore, the f is source free. Okay. So what does this tell you? Find the stream function for f, proceed the same manner as finding the potential function for f for a conservative field. Let g be the stream function for f. Then g of y, g little y is equal to y. So that tells us gxy is equal to y over squared over 2 plus h of x. So then we have so then that tells us so if we let c equal 0, then we know that gxy equals x squared over 2 plus y squared over 2. To confirm that g is a function of f, note that g of y equals p. Let me write that part over here to verify. little gy equals y equals p, and negative g of x equals negative x equals q. Notice that the source free rotation vector field, this is perpendicular to the conservative radial field, delta is perpendicular to conservative radial vector field delta G equal to xy. Alrighty, and then I'll show you the image. Okay. Okie dokie. Flying. Hopefully it feels like we're flying. Feel like it. All right, so vector field F is given as following. Verify the field is both conservative and source free. Find a potential function of F and verify the potential function is harmonic. So let P of X, Y equal to sine Y and Q of XY equal to e to the x cosine X. Nope, cosine Y, sorry. Notice that the domain of F is all to space. So domain all to space. So that tells us we are simply connected. All right, so therefore we can check the cross partials of F to determine whether F is conservative. So we want to note that P of X is E x cosine Y, which is the same as QX. So F is conservative. Since P of X equals e to the x cosine Y, and Q of Y equals negative e to the x sine Y, px plus qx equals 0. So that means the field, or F, the field is source free. To find the potential for F, let little f be the potential function, so therefore we're looking for this stuff again. So then we know f of little f is equal to e to the x sine Y. Integrating the equation with respect to x, we would have e to the x sine Y plus h of Y. So then what we also know is that f of y equals e to the x cosine y plus, oh, nope, that's it, that's for that one. Differentiating f with respect to y, we would have e to the x cosine y equal to e to the x cosine y plus h prime of y. So what we can take from that is that h of y equals 0, so that fxy equals e to the sine y, or not to the sine y, e to the x sine y, is a potential for f. Okay, so then to verify, for harmonic, take the partial, equals e to the x sine y, sorry. Keep wanting to throw an x in there. And then fyy again, I do. So then when we add the partials together, we get 0. This satisfies, if I could spell, satisfies the equation we were looking for. Okay, so technically 2 more problems. We have the next one, and then the one following that is the same problem, but we do it in 2 different cases. So yeah, very, 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 very close. Looks like my camera's just not working today. I'm very sorry about that. At least you get your problems. All right. Although, oh wait. So using Green's theorem on a region with holes, calculate the integral where d is the annulus given by the polar inequalities. Although d is not simply connected, we can use the extended form of Green's theorem to calculate the integral. Since the integration occurs over an annulus, we convert to polar coordinates. So what we would have is So then we end up with 15 pi over 2. Sorry. All right. Last problem. Using the extended form of Green's theorem, let f equal the vector and let C be a simple closed curve in the plane orientated counterclockwise. What are the possible values for the following? So there's two things we want to consider. First thing you need to consider here is that we use the extended form of Green's theorem to show that this portion is either 0 or negative 2 pi. That is, no matter how crazy the curve is, the line integral for f along C can only have two possible values. We consider two cases. The first case, the case when C encompasses the origin, and the case when C does not encompass the origin. So those are the two things we kind of need to consider. So this will be the first case. And that is the one where we consider C does not encompass the origin. So in this case, the region enclosed by C is simply connected because the hole in the domain of F is at the origin. We showed in our discussion of cross partials that F satisfies the cross partial condition. If we restrict the domain of F just to C and the region it encloses, then F with this restricted domain is now defined on a simply connected domain. Since F satisfies the cross partial property on its restricted domain, the field F is conservative on this simply connected region, and hence the answer is 0. So what do you have to remember and pull out from that? You restricted the domain, which then defined F as simply connected. And since it satisfies partial cross partial property, we also know that F is conservative. So taking those two things in mind, we know that is 0. Okay, so that is the first case. Did I have a picture for the first one? No. Okay. So for case 2, I'm not going to reread it, but it says, so this is case 2. So that means we are having C encompass the origin. In this case, the origin is closed by C is not simply connected because the origin contains a hole at the origin. Because the region contains a hole at the origin. So hole at origin. So not simply connected. Let C1 be circle of radius at A centered at the origin so that C1 is entirely inside the region enclosed by C. Give C1 a clockwise orientation. So basically, it's gonna have you do this in order to kind of get around it. So what we're going to find is all right, so then that tells us, I may end up making it a 10th slide, sorry. So what this tells us is so if we let C1, since C1 is a specific curve, we can evaluate it. Um, so then X is equal to A cosine T, Y is equal to A sine T, for 0 to T 5. So what that tells us is so that tells us and I think that's what we were allowed to have, right? Either 0 or negative 2 pi. Okay. So that